Hi everyone, so I'm Michael. Like Ronnie said, I work for AMD. I'm part of the Fortran Compiler team and also the OpenMP Compiler team. So I care a lot about OpenMP, but also I care a lot about Fortran. So I was delighted by today's keynote. And so I'm going to show a bunch of things about a project that we did together with the HPC department at Cinica in Italy about their STREAMS application. So it's not STREAMS as in the benchmark, it's STREAMS as in computational fluid dynamics. And we evaluated the performance of the AMD Next-Gen Fortran Compiler. And one thing I need to tell you is, by the time we wrote the paper and we got it approved, it was the Next-Gen Compiler. Since like 3 weeks ago, it is now the AMD Fortran Compiler for our GPU. So, the paper title has been overtaken by events. But anyways, all right. So what we're going to talk about is a bit about the Instinct accelerator and the ROCm platform, then the next generation, now Fortran Compiler STREAMS, the performance study that we did, and conclusions. All right, first, the application, the accelerator. So we were using the Instinct 300X accelerator. That is a discrete GPU. So we've been seeing talks about the MI300A, which is an APU, so unified shared physical memory. This one is a discrete GPU, so it has a host system. You can actually see it here. So there's the EPYC processors and then 8 of those GPU blocks. It has around about 300 compute units, 190 gigabytes of HBM, and it connects to the EPYC host processor via PCI Express Gen 5, and then between the individual MI300Xs, there is an infinity FFPD links so that all those GPUs can talk to each other and form like a big shared memory domain across the GPU blocks. All right. Now, regarding software support, and the shaded area is what I'm going to focus on. So AMD has 2 software stacks, one for the EPYC processors, which includes the AOCC compiler still on the old Flang compiler, and the ROCm stack, which includes our GPU software. This one, like I said, recently moved to the new Fortran compiler. But this is the software stack that has all the HIP programming models, the libraries for our GPUs, the machine learning frameworks are also in that space, and also the communication libraries that are meant to talk to between the individual GPUs. And this is what we're going to focus on. We're going to ignore the CPU part for today. And then specifically on the compilers, so like I said, both software stacks have their own respective compiler, and in this case, we are here in this space where it's 100% open source compiler. So we basically downstream from LLVM project, and everything that we do is also going back up eventually. So it's a really two-way collaborative effort between AMD and in this case, the Flang community. All right, and then one thing, because it was mentioned a bunch of times throughout this week when it came to Fortran compilers and the history of Fortran compilers in the LLVM project. So in about January, the LLVM project deemed Flang new, which was actually Flang new, to be production ready enough so that they can abandon the -new from the command line name, from the project name and everything. And they basically transition to say, all right, this is our new compiler going forward. There is no more old classic legacy Flang or whatsoever. And the new thing now is the compiler that we drive forward. And at that time, AMD also said, we're going to also do that transition, because the compiler really in the past 2 years evolved greatly, not only in terms of base language support, but also in terms of Fortran, GPU support in OpenMP. So now this is something that you can actually use and work with to get a reasonable outcome of your project or of your application work. And so this is also the reason why we're doing this paper, because now the compiler is stable enough so that not only we care about features, but also we now can start caring about actual performance and start optimizing compiler performance, and also see, you know, how well applications are working with that compiler. Okay, and like I said, you know, Rocket 7, which was released, I think, 3 weeks ago, has this compiler now as the default Fortran compiler. It still ships the old stuff, but you know, you now need to really work hard. Well, not hard, but you need to work to basically get the old compiler instead of the current compiler. All right, now let me give you a bit about Fortran. So Fortran is an interesting language. I don't know, you've been all at the keynote, so you've seen that it's not only interesting because it's a nice language to write in, but it also has a bunch of quirks that I want to show you, which kind of influence how a Fortran compiler works. So first of all, Fortran is case insensitive. So you see people still writing screaming Fortran code, meaning all caps, right? I was talking to one person a few months ago, and he actually told me that he's losing one finger while typing, so his pinky left finger is always on shift. So probably they need to adjust. And then, you know, just from a historic perspective, Fortran was invented before the Chomsky hierarchy in the 60s. And so also before subsequent parsing theory and parser generators have been developed. And you can actually see that there's like an inflection point in history of languages that have been invented before that happened, and languages that were invented after this happened, right? So they're completely differently designed, and they have different semantical and also syntactical structure. All right, here's a quiz. What's the difference between those two Fortran statements? There is. The first one has a dot, the other one has a comma.
Oh, okay.
And there's a bunch of blanks in there, right? So the first statement, that's an assignment to a variable whose name is comprised of the letters D-O-I, so it's DOI, even though there's white space in there. And the value that is being assigned is 1.10. And the other one, despite there is no blank in there, is a loop, a do loop, that it has I as the induction variable and counts from 1 to 10. And you know, this is the code that is out there, right? I'm not making this up, okay? This is not taken from an actual application, but you know, it's there. And then because of the large history of Fortran code out there, we still see Fortran code that doesn't have keywords, okay? So in C, int, void, all those words are keywords that have special meaning to the compiler. Fortran just doesn't care, okay? So this is a valid program in Fortran, right? Complex program equals 42, print star program end. Even worse, this is also valid Fortran. So you can write program else, end if equals 0, if end if equals 1, then if equals true, else if equals false, end if, write if, end program. Right? If you put Flang or G-Fortran into Fortran 19 mode, right? With freeform Fortran, this is not accepted, but there's old fixed form Fortran code out there, which was written initially on punch cards. That's where this is still acceptable, okay? So first thing the compiler does is it just get rid, it has like a first phase called pre-scanner, which basically puts the code into normal form. So all lower caps, all irrelevant white space removed, because you're not, you know, you could probably skip them anyways. So the compiler cannot rely on you putting it. And so it's all removed. And this is the source code that then the parser actually sees. All right, and then everything starts. So, you know, from the Fortran source code with OpenMP, it goes to the pre-scanner, the preprocessor, even though Fortran doesn't specify to have one. Flang obviously has a pre-processing facility. That gives us a character stream, like I was showing in the previous slide. And then this goes to the parser. that creates a parse tree. We do semantic analysis on that, so fill in types and type conversions and make sure that it's not syntactically correct, but also semantically correct. That gives us a parse tree with annotations, and that we feed into a first lowering. And what we get from that is high-level Fortran intermediate representation, where we still see things like, as this morning keynote, array syntax is there explicit. So the compiler doesn't just see do loops and unrolled stuff. They actually see the actual arrays and how they are processed by the programmer. And so we can do optimizations there. Then after that has happened, it goes into a second lowering stage that gives us Fortran intermediate representation. So the representation is still very Fortran-esque, and you can still see key concepts of Fortran being reflected there. And then everything is fed through the MLIR dialect conversion, which gives us an dialect that is still MLIR, but kind of reflects that we're targeting LLVM as a backend. And then eventually we translate that into LLVM, regular IR, and then spit it out. And everything that you see here is based on MLIR plus with different dialects, right? So all these are MLIR dialects. Then there's an OpenMP dialect where you can still explicitly see all of the OpenMP structure of your code. There's an arithmetic dialect that kind of reflects math. So that's a wild mix of things that are going on so that the compiler knows a lot about the code and its semantics. All right, so much for compilers. So the streams code, it's compressible Navier-Stokes equations. So basically what it does is it has like two basic modes. So it's a CFD code, right? But it can be used to simulate flows that have discontinuities. So that means where there's some sort of shockwave traveling through your fluid, especially when you simulate something like high Mach numbers, or you have like a sonic shock or something. This is where you need this special tree bands. And so this is a Fortran code, right? That's why we care about it, or I care about it. And so it uses MPI for the cluster parallelization. It uses OpenMP already for CPU. And for GPU, it has all sort of mix of things, like pretty much what we heard today also. It has CUDA Fortran HIP and also OpenMP Offload. And so what I wanted to find out is how much performance gap is there between OpenMP offloading and HIP, which was kind of the grand theme of this session anyways. So it sort of nicely fits in there. And can you be more productive by writing OpenMP without sacrificing too much performance? And here's just some use cases. So there's a shock wave hitting a wall, which is kind of an example of either the flow hitting a wing or a turbine inlet at high Mach speeds. And the other one is a flow plate, as far as I understood it, which basically is meant so that turbulence is sort of smoothened out so that the flow doesn't disconnect from your turbine plate or something. All right, so this is the kernel code. If you can't read it, so can't I. So I think the key thing here is there's a triply nested loop. I mean, we're sort of working in a three-dimensional space here, and there's already existing OpenMP targets to basically map the data environment and then distribute something across the GPU, and then we have those triply nested loops. And then the kernel code is pretty darn complex, and what I'm showing here is probably like less than 50% of the real kernel code. So you see a whole bunch of dots here that I put in because otherwise you couldn't just, it would all be gray, right? So basically what I'm showing here is like, so this is if at the current place there's a shock, so there's a discontinuity, then switch to the other implementation. If otherwise, do the smooth kind of solving without the discontinuity in the shock. Right. So this basically also repeats in there. So it's pretty much large. And the first time I was talking to the application engineer working on this, I said, well, let's simplify the kernel by pre-computing this. And then depending on whether you have a shock, do that or that. And he said, you have to re-evaluate that for each and every grid point. So there's no easy way to get rid of that central if and kind of reduce kernel complexity. All right, so system configuration, I'm gonna flash that for recording. I think the important part is that we don't do anything fancy down here, right? In terms of compiler options, this is just crank up the optimization level, turn on OpenMP, target MI300 ASD architecture, and then for HIP also use O3. So these are pretty much what they also use in production for the thing. And for the benchmark size, we fill up about 80% of the available GPU memory so that the GPU actually has something to work on. Okay, and then the first thing you will notice is that there's a bunch of kernels in the code that do different attributions of the computation. And so what we found is that the kernel execution time directly correlates with kernel code complexity. So that is kind of an obvious thing, almost like a knowledge bomb. If you have a really large kernel that takes a lot of time, it's reflected in the runtime. But it also helps you to basically focus on the ones that you probably care more about because they contribute more to the overall runtime than potentially some other smaller kernel that you probably can, at least at the first approximation, ignore for the first optimization target. Okay, and the thing is, this Vino scheme that they use is really computational intensive, so that's why they make the distinction between is there a shock and do we actually need to switch to the heavy method, or can we get away with the slightly less computational effort because the flow is still in an okay state. And then, another question is, if you have 3 triply nested loops, what is the correct order? You want them run them IJK, KJI, you have those 6 permutations, and so which one is the best one? And then secondly, the other question is, how many of those levels do you collapse, right? And if you go back here, you see we have like a 4.1K, 1.4K times 600 times roughly 700. So this is the number of threads that we have or work that we have to do in each dimension. And so the question is, how much do you collapse? Obviously, if you don't collapse at all, you get like 1,400 threads in one row. For an MI300A, to get every GPU thread busy, we need like on the order of 19,000 of them. 19,416 or something. Don't quote me on that exact number. It's a lot, right? So, one-dimensional collapsing doesn't work. So we need to collapse more. And as you can see, the more loops we collapse, the more work we have to basically saturate the GPU. And then the question is, in what order do you put the individual loops? And so, we basically did a study of what is the best loop nest for this GPU. I should probably say that there's previous works for other GPUs where a very similar study was conducted so that you can see, and compare what is the correct loop nest. And it seems like that, at least for this code and several of the kernels, the nesting that is good for other GPUs is the same as for AMD GPUs. So you don't have to necessarily, switch the loop order all the time. And if you have to, OpenMP has the interchange construct, which basically helps you do that without actual code change. And that's another productivity gain that I would like to point out. Doing this basically means in your editor, you just flip two loops in Fortran. If you would do the loop order exchange in HIP, that would be a lot of more work that you would have to do. Okay, so we picked 2 of those kernels, and then we basically tried to look more at how the whether the compiler can generate efficient code for all those loops. And it seems like, that switching things around for the 2 collapse levels that we picked, there is, for some kernels, a material difference. So that means the data access pattern actually matters. And then for others, there's like a gradual difference. So probably you don't care that much about, this kernel where, there's only a marginal difference. But here for that one, for instance, you actually care to pick the correct loop order and the correct collapse. And then, like I said, there's 19,000 threads available on the GPU, but they don't compensate for latency sort of automatically. So you try to oversubscribe the system by a factor so that you can compensate for memory access latency, for arithmetic latency in the execution units. And so, the other axis that we played with was what is the number of threads that we actually throw at the system? So how many threads do we put into a thread block? And it seems like that 512 threads gives the best for the convective kernels, which do most of the load. Yeah, and this is basically the same thing now for even more, right? We went down there, we went up above, and what you also will recognize is there's like hardware resources, and hardware resources are usually fixed in their size. So there's like 256 vector registers on an AMD GPU. With 512, it seems like that you can get enough vector registers used and enough load on the system so that you can compensate for latency without causing too much spill, because you need to move out of the vector registers back to memory and swap back and forth, which is the case if you use more than 768 of those threads. All right. And then, the central question that I wanted an answer for is, do you have to use HIP in this application? And, do all the transition from Fortran, writing a bind C interface so that you can call C code, and then from C code go to C++ so that you can invoke HIP from there? And the answer is, well, it depends a bit on the kernel that you're looking at, right? So one is best possible, one is the original OpenMP performance. Black is the best OpenMP setting that we found for that kernel, and HIP is the performance, is the kernel time that you would get when you would write that in HIP, like they would do in production. And lower is better in this case. And as you can see that, there's like a few kernels where you're like at 80, maybe 75%. HIP is 75% of the runtime compared to OpenMP. But there's also kernels where you're pretty close, like in range of 90%. And then it really becomes an informed question whether you are willing to pay 10% of your application performance, or in this case, kernel performance, if you can then stay at a high productivity language like OpenMP. And I guess, at least for me, life is a lot easier with OpenMP, so I would probably go with OpenMP. And then, when I really see that this kernel here is the one that really affects my overall application performance, I can pick that kernel, write that in HIP, and keep the rest of the application in OpenMP. So I think this is a promising result that I'd like to see more for other applications as well. Okay, so in this trail of papers that have been written together with Chinica by various vendors, OpenMP has shown good performance portability across several those papers, right? So there is some portability that you can get, not only from a functional perspective, but also from a performance perspective. When you look at the configurations, the previous works was using the Intel Fortran Compiler and an Intel GPU Max. We are pretty darn close on how the AMD system behaves with respect to what it was done there. So that's where it's easy to move between this software stack and hardware stack towards the AMD stack. And we've seen for the complex kernels, about 15% less performance than with the HIP version. And like I said, at least to me, this is in line with, okay, I can switch to productivity mode instead of performance mode and let OpenMP sort it out for me. And there's even one case, I didn't specifically point to it, where OpenMP even is better than HIP. So, it's even something that could happen, that the compiler can infer some more about what it knows from OpenMP. And with that, I'm done. Thank you.
Question. Sorry.
The graph, could you go to the
Which one?
19.
19?
Yeah, that's it.
Okay.
Why is the OpenMP best OpenMP worse than original OpenMP? The first one and there are two.
That is a very good question. I don't know the answer. That's something that Giacomo did for me. I would have to look at the data again. Sorry.
So is it like best OpenMP overall with your configurations as opposed to?
Probably, yeah. Sorry.
Kernels vary, but because the amount of time you're executing kernels, like, so maybe that kernel's hardly ever executed. Kevin?
Yeah, thank you for the presentation. In this first kernel, do you think that would be interesting to try the extensions that are being discussed in the committee? Do you think they would impact?
Yes. So there is, let me see if I can find the slide real quick. So there are actually, there's like these guys down here, right? So these are like local arrays that are filled within each thread. So these are definitely arrays where you could use the equivalent of double under shared double under, or group private, potentially not dynamic group private, but at least group private memory, which we don't do because Flang does not yet support that. But there's certainly some performance uptake that we could achieve there.
Okay. Thank you.
Eric?
You had a piece of code where you had like that collapse tree, and then you were testing all the permutation of it. Is there a reason why the compiler can't guess the right version? Because I feel like that should be the compiler's job and not the compiler's job.
Yes, eventually the compiler should be able to infer that. So in history, I would say, there have been compilers who were smart enough to figure out that you unrolled your loop, you picked a certain loop nest in that unrolled loop, and then the compiler would re-roll everything, change the loop order, and unroll again, right? So that's all possible. And eventually, I hope that Flang will get there. But like I said, we got Flang stable enough throughout 2024 and 2025, of course, that it's now close to production readiness, together with the community, by the way. It's not only AMD work. And so now is the time to start looking into actual optimizations and what the compiler can do to improve performance.
So it's not a language problem, it's the compiler's not there yet.
It's not a technical problem from a perspective of compiler technology. It's a technical problem because somebody has to do it.
Maybe it's related to that question as well. Does the lowering in MLIR use like dialects like affine, linalg, one of those dialects that they try to do optimization at that level?
No. Right now it is what is reflected in MLIR in Flang is the Fortran structure, if you will, like allocate, deallocate. There is do loops, do concurrent loops. That's the Fortran dialect. There is the arithmetic dialect, which basically covers things like math functions, floating point strictness. And then there's OpenMP, which basically reflects the OpenMP structure. So this would be reflected as a OMP target, OMP teams, OMP distribute, OMP parallel, OMP do sort of nesting. WS loop, it's called. So the nesting is there.
And then all of these, they go down to LLVM and LI.
Right, and eventually, compared to Clang would basically take the front end, and right after syntax analysis and a bit of semantics analysis, it would throw out OpenMP and replace it with runtime system calls, right? In Flang, we basically do it very late in the compiler stage. so that we can do optimizations on top of the structure that we still maintain in MLIR, so that we can see what is the actual structure of OpenMP that you wrote. But then eventually, yes, at some point we cut, and then we spit out KMPC, I don't know, _Peril_51 to actually launch a Peril reach. So then it's regular LLVM code.
When I see this piece of code, it seems that you are using a lot of local variables in the code.
Yep.
On the GPU. Do you know if it limits the number of waveforms that are launching, that are able to be launched in parallel? And is this the limitation factor?
Well, that's where I said, at some point, if you crank up the number of threads too much, you exceed the amount of memory that you can keep in the vector registers of the GPU, and then you start spilling, right? Other than that, this code does not use much of LDS storage, as we call it, because the compiler does not fully do that optimization yet, and we don't have support for group private, like I said before.
Okay, Johan?
A relevant question too, for that 50% on the gap, do you see any, like, between 2 OpenMP from C-line or F-line and HIP? Do you see anything that people manually write in 2 HIP, but hard, could be hard for compiler to do transformation, right? Any like maybe you share memory or other feature?
Of course, yeah. I mean, the thing, of course, is OpenMP wants to be portable, right? So this assumes that you don't do anything nasty in HIP or in CUDA, where you use like HIP or CUDA built-ins or something like that, right? Which we cannot really reflect in OpenMP at this point. Dynamic group private, for instance, is one way to get one of the most used features, I guess, in OpenMP reflected with double undershared and dynamic LDS memory. And with kernel language, we will certainly also approach more of those features, right? But I think there's a good chance that there will always be some features that you could express in the low-level language that you cannot fully express in OpenMP. And I would also not claim that a compiler will always be able to automatically exploit those features. We may be able to recognize some of the patterns. Like, for instance, Clang today, if you create a variable or a small array inside the Teams construct, then it already recognizes that this could probably go into LDS, and it will allocate it in that memory space. That sort of thing, I guess, is sort of always possible. But then still the question will be, is it always the right choice when the compiler makes a choice and says, this is not going to go into that fast memory space.
All right. All right, well, let's thank Michael again.
Thank you.